Hey, welcome to question 3 of the problem solving session that corresponds to chapter 7, where we're looking at elimination reactions as a major theme of that chapter. So in this particular problem, you are asked to provide the major E2 reaction product and the mechanism for each of the following reactions. As with all of these videos, I highly recommend that you first go onto Canvas, go to the Files section, and download this worksheet and attempt it on your own before going through these solutions. Or alternatively, if you feel totally lost when you start into these problems on your own, go through this video to walk through the first part of the example with me, part A, for example, and then hit pause and try parts B and C on your own to make sure that you're getting the hang of how to do these problems independently. So going ahead with part A here, 2-chlorohexane reacted with sodium methoxide, NaOCH3, and ethanol. We will go ahead and work through this problem. So I'm going to start by drawing out the structures of our reactants. So 2-chlorohexane, we need a 6-carbon chain. So go ahead and plug in that 6-carbon chain, and at position 2, chlorine, it doesn't specify whether it is an R or S configuration at this stereocenter, so we'll just draw it with no stereochemistry indicated there. And then sodium methoxide and ethanol. So what is going on here is that we can think of the ethanol as being the weaker of these two bases here, sodium methoxide and methanol. And since methanol is the weaker of those two bases there, we can think of that as our solvent, and the sodium methoxide is what's going to be acting here as the base, because certainly if you have multiple ingredients in a reaction and more than one of those could act as a base, the one that's actually going to be doing the work, acting as the base, is going to be the one that is the strongest base, the most reactive base. So sodium methoxide, since we have sodium there shown adjacent to our oxygen, that indicates to us that this is going to be an ionic bond because there's a huge electronegativity difference between those two. So in solution, what you would actually have is sodium cation and the methoxide with a negative formal charge on that oxygen. So the oxygen certainly is what's going to act as our base here, because that has the negative formal charge. It's the least stable of anything in the reaction mixture. And then you could think of the alkyl halide as acting as the acid here. And in an E2 reaction, that's what we're specified that we need to give a product of here. What is always going to happen in the E2 reaction is that this is a one-step mechanism where the base is going to come in and grab a proton from the beta position, that is the position that is adjacent to the carbon that has the leaving group. So our carbon with the leaving group is right here. This chlorine atom is our leaving group because that's the electronegative atom. So our hydrogens that are up for grabs here going to be either protons here at the methyl group or our methylene CH2 group there. We always want to follow Zaitsev's rule whenever doing an elimination reaction. Zaitsev's rule says that the preferred product of these reactions, the major product of these reactions, is going to correspond to making the most alkyl substituted alkene product that we can. And you can do that by removing a proton from the most alkyl substituted proton here. So methyl group versus methylene there in our starting materials. Definitely the site for removing a proton is going to be right here because that is our more substituted position, and it's going to lead to the more alkyl substituted product. So let's go ahead and write out this mechanism. I'm going to sketch it out actually over here to the right because I've scribbled too much on that info at the left. So drawing my structure out, I'm going to show here at our position with the leaving group, I'm going to go ahead and show both of those hydrogens explicitly for now so that I can illustrate one of those being broken away by our base that comes in. So methoxide is our base coming in. And the methoxide base comes in, grabs a proton from our alkyl halide acid. That forces this in red carbon-hydrogen bond to break. Those electrons have to go somewhere, and where they are going to land is coming over here toward our leaving group, because that bond to the leaving group is relatively weak, and when the leaving group breaks away, it yields a relatively stable halide product. The halogen is pretty happy to have a negative formal charge on it because it's a very electronegative atom. And so ultimately, as a result of these three electron pushing arrows, what we will generate in this E2 reaction is our alkene product following Zaitsev's rule there. So that leads us to the end of our pathway being this E2 reaction product. We'll go on to the second problem here, approaching it the same sort of way. And in this, we have butane as our 4-carbon chain. At position 2, we have both a chlorine and a methyl group, so we'll do their chloro, 2-methyl. And then we have sodium ethoxide and ethanol here. Same thing as above. The strong base here is what we're going to focus on, acting as the base that grabs a proton from our alkyl halide acid. So we have here, and I'm just filling in the lone pair electrons to get my mechanism as detailed as possible here in this E2 reaction. So our oxygen comes in, going to grab a beta proton, and the one we want to go for is going to be one of the ones right here. So I'm going to show one of those explicitly. Attacks there. And then that forces the carbon-hydrogen bond to break, and I'm showing those electrons coming over using that green electron pushing arrow to make the double bond, as our weak link, our bond to the halogen, breaks to give us our alkene product out of this, our elimination product. And now we specifically chose to remove this proton rather than removing other possible protons here and here at those methyl groups I've highlighted in yellow, because by removing at this position the more alkyl substituted position, we will create the more alkyl substituted product. This product here at our alkene group has 3 direct bonds to alkyl groups, 1, 2, 3 dotted there in yellow, making it a much more substituted product than if we had removed a proton from our methyl groups over here at the far left that I'm further highlighting there. So with that, we will go on to part C here. And in part C, we're asked to take 1 bromo, 1 methyl cyclopentane, react with sodium ethoxide in ethanol. By the way, the sodium ethoxide, NaOET, recognize that the ET here refers to an ethyl group, in other words, CH2, CH3. So we have the same reactant base here as we did in part B. We've just spelled it out a little bit differently, but don't let that trip you up. So cyclopentane, 5-carbon ring, 1 bromo, 1 methyl, and then we'll plug in our sodium ethoxide. Remember that if we're thinking about this as a mechanism, we can think of the sodium as being a cation, oxygen anion, and I'm going to abbreviate our ethyl group there as OET. And then at this point we need to, since this is an E2 reaction, we were given the problem, that's what we're to do here. The oxygen anion is going to come in, and it's looking around for a beta proton to remove. Our options here are going to be removing one right here, over here, which is symmetrical to that first one that we drew out in red, so just do one of those two. Or a third possibility would be the methyl group there. Now, as before, to follow Zaitsev's rule, we want to always remove a proton from the more alkyl substituted alkyl halide position, so that's going to be right here, or alternatively at that other CH2 group that's symmetrical, doesn't matter which. So we remove the proton there, that's going to force this carbon-hydrogen bond to break. Electrons from that come down, as our very nice, very capable bromine leaving group leaves. The bromine is a very capable leaving group because it's a very electronegative atom. It is going to be quite stable and happy on the product side of this equation here as a bromide anion. So it's giving us a relatively stabilized product. So that gives us our 5-membered ring, alkene group in there, And our other product of that reaction would be our protonated ethoxide. And you'll notice that, as no coincidence, ethanol is the solvent here, and ethanol is also what we've generated here as a result of this reaction. So with that, we conclude our coverage of this problem. We're focusing on drawing the E2 elimination reaction product that results from reacting an alkyl halide with a base. In this one-step mechanism, we remove, using a base, the beta proton. Boom. At the same time, the alkene group forms by taking the electrons from that carbon-hydrogen bond and moving those down, and the leaving group leaves. And the leaving group is really at the heart of this because you have to have a relatively weak, relatively favorable bond to break here in order for this process to occur. You can't break a carbon-carbon bond away, so the carbon-bromine bond is the site that gets targeted here because that's going to yield a relatively stable product by breaking a relatively weak